Hello, in this part of the video, we will be working on energy diagrams. An energy diagram is a representation of the energy changes that take place as reactants are converted to products. Okay, so for example, if you have a reaction AB plus C, say if C is a negatively charged species, then the reaction proceeds to give A minus and BC. Okay, so here what is happening is the bond between A and B is broken and the bond between B and C is created. So we can create an energy diagram by plotting the energy on the y-axis and reaction progress or reaction coordinate on the x-axis. Okay, so and reaction coordinate. So this reaction can be represented, say, in this manner, where here are my reactants, okay, and here is my products. This part of the graph is called as represents the transition state. And in the transition state, it's a very high energy state because the bond between A and B is partially broken and the bond between B and C is partially formed. Okay, so this is the top of the hill and this represents the highest energy state. Okay, so here these are my reactants and these are my products. Okay, all right. So if you look at this energy diagram, it looks like the reactants are at a slightly higher energy state than the products which are at a slightly lower energy state. The energy that is required to reach the transition state is what is called as the energy of activation, which we can represent as A. Okay? And the difference in energy between the reactants and the products is represented by delta G, okay, which is your free energy change when the reactants are converted to products. Okay? Now, the energy of activation tells us whether the reaction would go slow or fast. If we have a large energy of activation, then the reaction is slow. Okay? So, if EA is large, then reaction is slow because you have to go over this higher energy barrier in order to reach the products. If EA is small, then that represents a reaction which is fast. The transition state is usually represented in this manner, where you put dotted lines between A and B and then dotted lines between B and C, which tells us that this bond is being broken and this new bond is being created. Okay? And since we have A minus, so we can put that it is slightly getting a negative charge, and here C had a negative charge, so it also has a slight negative charge. Okay, so this is a stage which represents our transition state. So this is how you represent an energy diagram. The energy diagram speaks a lot about how what kind of reaction do you have. For example, if you have a energy diagram which looks like this, okay. Again, don't forget to label the axis, energy on the y-axis and reaction coordinate on the x-axis. So if you have an energy diagram that represents like this, again, this part will be labeled as energy of activation. Here is my reactant and here is the products. Now what does it tell about the what type of reaction do we have? We'll see that the EA is quite large, so it should be a slow reaction, and also the difference in energy between the reactants and products, which is again delta G, is a positive quantity. So these type of reactions are called as endergonic reaction. Okay. Now how can you represent an exergonic reaction? Where the reactants are at a higher energy state and the products are at a lower energy state. Okay, so this is my reactant and this is the product, and if you see the delta G value is negative, which represents a exergonic reaction. And in our last video we saw that delta G is to be negative is what is favored. That means this reaction will be occurring spontaneously. If we have a energy diagram which is represented like this, okay, where if you compare these two, okay, again I forgot to label this energy and reaction coordinate. Okay, so what can you say about the energy of activation in this one? Coordinate. So if you look at this energy difference between this and this is smaller as compared to the energy difference between this and this, right? So that means this reaction would be a little more faster than this reaction that's represented here. Okay? Now, if you have a two-step reaction, then how will we represent the energy diagram? Okay? So let's try an example of a two-step reaction. So again, say for example, we have the reaction AB plus C minus gives A minus plus BC. So in this reaction, this bond is again being broken and BC is being formed. Okay? But maybe this reaction takes place in two steps, where in the first step maybe AB breaks down to give A minus and B plus. Okay, so this might be my intermediate that is formed during the reaction. Okay, and then so this is step 1, and then in the next step B plus, which was my intermediate that was formed, reacts with C minus, okay, to give BC. Okay. So in the first step is where you have an intermediate formed, and then the intermediate immediately reacts with the reactant C in order to give the product BC. So if we have to draw the energy diagram of this two-step mechanism, then in step 1, the energy diagram, so again remember we have y-axis energy, x-axis reaction coordinate. Now in this case, if you see, the first step should be endothermic because you need energy to break the AB bond, right? So if we draw this out, the first step may look something like this. Okay, where this is my AB and here is my B plus, which is my intermediate, and it's a energy requiring process. So that's why the difference in energy between these two should be positive. Okay? Delta G is positive. And the energy of activation is also pretty high, which tells me that this should be a slow step. Okay, so this first step is a slow step, which is the formation of an intermediate. Now how will my second step look? The second step, again energy versus reaction coordinate. The intermediate will be at a higher energy state, and then the product will be at a lower energy state. Okay, so this is my B plus, and here is my BC, and this is my transition state. And the difference in energy between these two is a negative delta G, which means it's a spontaneous reaction. Now the energy of activation between these two is lesser than the energy of activation between which we saw in the first scenario, right? So that means the second step will be a fast step. The first step is my slow step. Now if I combine, so one more thing is that the slow step will also be my rate determining step. Okay? It will also be my rate determining step. Always in a multi-step process, the slowest step is the rate determining step. Now we can actually combine these both into one single energy diagram, because it's overall one single reaction, right? Which happened in 2 steps. The mechanism shows 2 steps, so we can draw the energy diagram corresponding to the 2 steps here. But then finally, we can combine both of them into one energy diagram, which can be represented like this. Again, energy on the y-axis and reaction coordinate on the x-axis. Here we have the reactant forming the product, which was my B plus. This is an intermediate product, and then the final formation of my product BC. Okay, so we have BC, here we have AB, here we have B plus. Now this is my transition state 2, my transition state 1, and the energy of activation, this is A1, and the energy of activation for the second step is EA2. And the overall energy difference between these two is delta G, which is a negative quantity. So the reaction is overall exergonic. Okay, the first step was endergonic, second step was exergonic, and overall, because delta G is a negative quantity, the overall steps are exergonic. So you can actually figure out how many steps a reaction has by looking at this how many hills you have on your energy diagram. So if you have 2 of these, that means it's a 2-step reaction. So for example, if I had a energy diagram which was represented like this, then since you have three energy transition states, this represents a 3-step reaction. Okay, so this is how you can draw the energy diagrams for 1-step, 2-step, or multi-step reactions. The kinetics part we'll talk about in the next video.